Welcome to module number 23. In the previous two modules, we talked about dynamic programming and linear programming. Now we're going to talk about convex optimization. The key thing that we're looking at here is a convex function. We have a space script x, and we have a function f, or in our figure g, from the space script x to the real valued numbers. And on the right-hand side, the horizontal axis is the input of the function, and the vertical axis is the output of the function, g in this case. And the function on the right-hand side has a cap sort of appearance, and it's called a concave function. Whereas on the left side, the function kind of looks like the bottom of a bowl. So top of a bowl, concave, bottom of a bowl, convex. And this allows us to define the functions formally as follows. So imagine that you have two locations, x and y, in the set script x. Okay, so x and y are two locations. And I will take any number lambda strictly between 0 and 1, and you'll take some combination of x and y. Okay, so let's say that this would be perhaps 0.4x plus 0.6y. Now, you can, at that value, you can try to imagine the function in two different ways. One is to evaluate the function exactly at that lambda x plus 1 minus lambda y. And this f of lambda x plus 1 minus lambda y will always be the lower point. And above it, we're going to have, so this is f of x, and this is f of y. And if we connect f of x and f of y on a line, and we give lambda weight to f of x and 1 minus lambda weight to f of y, and we get this thing. And this second expression is always greater than or equal to. That's the formal definition of a convex function. Concave, on the other hand, very similar, except that the connecting line is going to be less than or equal to the function. And therefore, the function is going to be greater than or equal to the connecting line. So just some notes. First of all, a function is f is convex if and only if negative f is concave. Secondly, convex and concave functions, you can evaluate this, and they have positive or negative second derivatives respectively. Now, they have a lot of properties similar to linear programming. Many real-world problems can be well approximated by convex. But one of the very nice features is the local optimum is going to be a global optimum. So here's the basic convex sort of problem. X star, the optimal location x, is going to be the argument of all the x's in the set script x over the function f of x. Now, it's important to realize f of x is concave, but script x is, I'm sorry, convex, not concave. F of x is convex, and script x is also convex. What this means that in script x, if we take any two locations in script x in that set, and we form a line between them, so again, lambda would be between 0 and 1, anything on the line is also in script x. That's the definition of a convex set. So that's one way to have a convex problem. And another approach is as follows. You're minimizing, again, f of x, subject to a lot of functions gi of x being less than or equal to 0. Now, they could be multiple gi of x's, they could be a single g of x, but similar to before. So this g of x or gi of x less than or equal to 0 is implicitly defining a convex set. And within the convex set, we're searching for the location x star that minimizes f of x. So you could ask, why is it interesting? Well, I already told you that one, at least mathematically cute thing, is that a local optimum happens to be a global optimum. And that's, that's helpful. It means that we're not going to get stuck in a local optimum by mistake. But again, many problems can be posed as convex. So for example, linear problems, linear functions are actually convex. They're both convex and concave. And because of that, linear programming can be posed as a convex optimization problem, and a feasible solution, a feasible algorithm for solving linear programs involves convex optimization. Another problem that can be solved with convex optimization is entropy maximization. The entropy is a convex operator, and therefore optimizations can involve convex optimization ideas. Finally, another sort of direction is least squares, where we're trying to provide an explanation to data that minimizes the residual or unexplained part of the data. So how do we solve it? One approach is Newton's method. Newton's method finds roots to the following equation: gradient of f, or derivative of f, is equal to 0. So the standard Newton's method that you may have learned in calculus finds roots, f of x is equal to 0. But now, because I said that the second derivative is going to be, depending on whether your function is convex or concave, it's going to be positive or negative. Therefore, we want the derivative to be 0, and at the derivative or gradient being equal to 0, that's where we have the optimum. So how do we solve this? Let's think about a Taylor expansion. We have a function ft of x, which is equal to f at one specific point xt, plus the derivative f prime multiplied by the distance delta x between where we are now and xt, plus half the second derivative times the square of delta x, plus higher order terms. Now again, we want to find the root of the derivative. So we want f prime plus f double prime, the second derivative multiplied by delta x, to be equal to 0. So what we're going to do, we begin at this point in the sketch, and then we by looking at the derivatives, it's sort of like drawing a tangent. We go from x0 to x1. x1 is where we believe, based on the information at x0, that derivative will be 0. And then we go from x1 to x2, and from x2 to x3, and so on. So Newton's method is quite simple, but the problem is that the convergence is on the order of 1 over t. So what do I mean by that? If you run t iterations, then the error, how far you are from the true x star, is typically going to be on the order of 1 over t. So in order to get somewhat close to x star, you don't need too many iterations, but in order to get very close, you need a great many of these iterations. So Newton's method is slow. What do we do instead? A second order method involves looking at the next derivative. So earlier, the challenge was that the first order approximation to the derivative slowed down Newton's method, and we use a higher order approximation. We not only use the derivative and the second derivative, we also used the third derivative, and we basically were trying to find a root of the derivative given the second derivative and the third derivative. Now, things can get more complicated with second order methods. For example, if you have a multidimensional function, then it's not a derivative anymore, it's a gradient, and the second derivative becomes a Hessian. And so basically, second order methods are faster than first order methods, Newton's method, but they're more complicated. So let's discuss one specific style of convex optimization called gradient descent. So in gradient descent, in each iteration, we're selecting a direction, and we're going to pursue that direction and move along that direction and try to improve where we are in terms of the function. So here we have a function, we have contour plots, and the contour plots are locations where the function takes the same value. And in the middle of the function, where it seems to be the origin, we have the optimal value of the function. And what's being shown here is that we start at this location, and we move around in some direction, and we move and move and move until we've optimized the function as much as we can along that direction. Now, there's this interesting property that when we've optimized it along a line, that means that now along that line, the gradient is 0. And we want, hopefully, to move in a direction where the gradient is large. We want to move down quickly. So to do so, the gradient is 0, or rather the rate of change along a certain line is 0. That implies that that line is orthogonal to the gradient. Okay, so every time one approach would be to try to find the gradient. Another approach is that we'll move along one of the coordinates. There are different ways how to do this, but the bottom line is that we're finding a direction to move on, and we move along that direction as best as we can, and then we find another direction. Now, how far should we move along that direction? Maybe we'll move, as I described here, as best as we can. However, there are functions, as you can see here, that each iteration we're moving maybe 10–20% closer to the origin. So we have geometric rate of convergence, but there's still maybe ways to improve this. So if, for example, when we're at this location, if we pursued that direction, we could zoom straight to the origin. But if we're pursuing, in this case, the coordinates, our rate of advance is much slower. So how do we, once we have a direction that we're pursuing, could be the gradient, could be a coordinate, could be anything, okay? How do you move and find a good location on that line? So this is called line search. This is a sub-method within gradient descent that you move along the direction just enough to minimize the function along that line. So a line search optimizes along the line, and there are a lot of variations on this. So let me describe them briefly. So one such variation is binary search. You'll know in advance, suppose that somehow, doesn't matter how, you were informed that the optimum along this line, and I made a squiggly line, but imagine that it's straight. The optimum along this line is somewhere between x and y. So what do? We look at the point straight in the middle, z, and we ask, is the value of the function larger than the value at x, larger than the value at y? What's going on here? So we evaluate f of x, f of y, and f of z. Okay, so there will be situations where, let's say we want to find the minimum. If we have a convex function, and if f of x is less than f of z, which is less than f of y, that implies that the optimal location is between x and z. So we're using these types of ideas to kind of perform function evaluations. And as we perform function evaluations, we're narrowing down the range of where the optimum can be. Now, instead of binary search, where every time we can advance by a factor of 2, a golden rule search, which you can go and read about, allows us to advance more efficiently. So the ratio of the number of function evaluations that you're going to need to calculate versus the narrowing down of the range of where where the optimal point can be, that ratio is more favorable using the golden rule search, and you may want to go read about it online. So on the course webpage, there's an example, and we coded it up. You can go take a look at a MATLAB version and a Python version. And I suggest that, it'll be helpful for you to do that, and it'll be helpful for you to try it out on some convex function. And if you want an example of a convex function, so an example could be that f of x is, let's say, quadratic, okay? So x squared is a convex function. So that'll be it for module number 23, and we'll continue next time.